All right, so we are continuing our sample problem, our example, and we're beep in the background. That's nice. Uh, if you have not watched the previous video where we did the directed network, I suggest you watch that first because we'll just build on that to see what the differences are when we move to an undirected network where I can travel back and forth along these edges. So that is what number two is about. Same weights, same network, except we remove the direction requirements, therefore making it a brand new network technically. So I'm not going to start from scratch. I'll start with the answer to the previous question, and then we could just focus on what's different, how should this be adjusted, and a lot of it is the same. While I'm thinking of this, I apologize if the previous video apparently had the worst mouse cursor ever being white. I can't go back and record that another hour. Hopefully it's not too bad. Hopefully this blue one is better. It was black on my screen, I promise, but apparently it did not record. But you could see the faint lines of the pointer, so hopefully it's manageable. I apologize for that. Let's get going. So this is number two. It's exactly the same as the previous one. I'm just going to recycle that answer. I wouldn't do this from scratch like this, but I want to emphasize how does this, where are the differences if I compare the two? So I want to have this as a reference, which is going to look a little different than if I did it from scratch, but it's okay. Okay, so my variables are pretty much the same because what is my decision here? I have to decide, am I traveling along this edge, yes or no? Traveling along this edge, yes or no? But I can now travel in two directions, and I have to have separate decisions for those directions. So instead of in the previous one, let's move this up a little. In the No, I don't have it anymore. Over here. There we go. In the previous question, I had a direction that I could only go from 1 to 2. I'm essentially just doubling that. I can go 1 to 2 or 2 to 1 now. So on each of these, or behind each of these edges, is one going one direction and one going the other direction. So each undirected edge that I see here is really going to double up to two directed edges, 1 to 2 and 2 to 1, because I can travel in either direction. And therefore, I need a decision for each one of those. Let me just double check that I'm recording. Yes, it looks good. Okay. Just paranoid. I talked for an hour and then, whoop, you actually didn't record. Sorry. So I just wanted to check. Okay, so we're still going to have our xij meaning, have the same meaning, that decision variable. It's going to represent the number of times I use the line 1 to 2, or I travel from 1 to 2, and 0, of course, if it's not used. The only issue now is that I have both directions. I have 1 to 2 and 2 to 1. Okay, so my adjacency matrix is going to be a little expanded. Still the same nodes, but 1 to 2 had a weight 65. 2 to 1 also has the weight 65. There's two different directions I can travel. So I really just double up from the directed version, but it's giving me more options and more decisions to make. Let's stick to 1. 1 can go to 3, but 3 can also go to 1 with a weight of 52. 1 can now go to 4, as well as 4 can go to 1. So it's very important, just to emphasize again, that you build this understanding on top of the directed version. So By that I mean be completely comfortable with how we handle the directed version before you focus on the undirected version, because the thought processes are the same. Everything is just more options, more variables, but the underlying logic is the same. So one can only go two, three, or four, therefore only those three, right? Not five or anything like that. Two can go back to one, we've said, and can go to four with a 32 edge and can go to five. Three can go to one with a 52, four with a 37, and six now with a 78. Previously, the direction didn't allow me to do that. Now it's an option. So I just go through them like that. 4 can go to 1 now with a 91, 2 with a 32, 3 with a 37, 5 with a 56, I had that, 6 with a 31, and 7 with a 28. Then 5 I can go to 2 with a 76, 4 with a 56, and 7 with a 38. From node 6, I can go to 3 with a 78, 4 with a 31, 7 with a 47. And from node 7, I can go to 4 with a 28, 5 with a 38, and 6 with a 47. So if you compare the two, there's just more of them now because I can travel in both directions. But the setup is very similar in that I have my adjacency matrix, which now perhaps better clarifies the network that it corresponds to. So again, don't look at this if you haven't looked at the previous video. So now I have a variable for each of these weight entries in my adjacency matrix. There are more of them. So writing out the objective function in detail is quite tedious. Quite tedious. It's going to go off the screen and it's going to waste so much time. I know the structure of it. I'm going to get rid of that. And I'm just going to do the alternative way. I know the structure of it. It's the weight of the decision, if you will, times the decision variable. If I'm going to travel from 1 to 2, let's make this bigger. If I'm going to travel from 1 to 2, it's going to cost me a weight, or a cost, if you will. Yeah, it's going to cost me 65, whatever that 65 might mean. If I travel later on from 2 to 1, that's a separate move, which happens to also cost me 65. So the objective function is the sum of the weights times the corresponding variables for every weight that has a positive entry in the adjacency matrix. Because I've expanded the adjacency matrix, I have expanded the decision variables as well. So I can be efficient in my formulation, but I have these other things to clarify it, and I'm still writing it in a way that is as clear as possible. Do not be sloppy here. The question is, can I give this to someone with a decent amount of skill that they have, right? They can understand what I'm reading, what they're reading rather. Can I give this to someone? They read it and clearly understand what this situation looks like. I still want to be as clear as possible, but at the same time, I want to be efficient. Okay, so let me move this down while we go up to our constraints. These are simply from the previous problem, right? I have to update them. I have to check. So let us maybe get rid of all of these so they don't confuse us. I again will look at the internal nodes because I still have a starting and an end node. Internal nodes. Let's look at node 2. The difference now is that I can travel from 2 to adjacent nodes and travel towards 2. There's no restriction anymore apart from what the neighbors are for that node. So last time we did, uh, I guess, from versus to, right? Is that what we did? From versus to. Yes. Okay. So let's do the same thing. From, no, is that what I did? I want to be as consistent as possible. Node 2, we traveled to node 2 and then from. Okay, so sorry, I added backwards. Just to, when you compare them side by side, to be as consistent and easy as possible. So into 2 versus out of 2. Okay. So into 2, I can go from 1, or I can go from 4, or I can go from 5. And I want to compare that to out of 2. Out of 2, I can go back to 1. I can go to 4. I can go to 5. So for example, x52 and x25 are completely different decisions, completely different ways of traveling between those two nodes. So now how do these compare? Well, for an internal node, I still have to count the number of times I visit the, the node, the number of times I go into the node has to be equal to the number of times I leave the node. Otherwise, I would get stuck there. So they have to equal each other. I can then rephrase that by simplifying, moving everything to the left, and you'll see that the the edges traveling into the node in question, node 2, they get a positive coefficient, can go into it via 4, can go into it via 5, and then the nodes, not the nodes, sorry, the traveling out of the node 2 will be a negative x to the 1, negative x to the 4, negative x to the 5, and only thing left on the other side is a 0. So we can do this, and we'll just shortcut that since these are going to get a little longer. Let's do that. So I'll just do this version. Look at the previous video for a longer explanation, but you do have the option of how to write this. Ultimately, for solver, we have to move all the variables to the left. So node 3, let's go through them one by one though. Into node 3, 1 to 3. I'm going to squish them. Well, this one doesn't need to. It's not that long. Into node 3 via 1, 1 to 3, or 4 to 3, or 6 to 3, minus leaving it 3 to 1, 3 to 4, 3 to 6. They have to balance out. The number of times I enter node 3 minus the number of times I leave node 3, they have to be 0. Those two numbers have to be the same. because I don't stop. That's not the end of my journey or the start. Node 4 is a little longer. Let's do it. Coming into node 4, 1 to 4, 2 to 4, 3 to 4, 5 to 4, 6 to 4, 7 to 4. Take away the number of times I leave 4. I leave it via or going to 1, 4 to 1, 4 to 2, 4 to 3, 4 to 5, 4 to 6, or 4 to 7. Those two numbers have to match. The number of times I come into the node versus the number of times I leave the node. They have to be the same for an internal node. So the underlying logic and reasoning is the same. I'm just not as restricted as I was in the directed case. Node number 5, coming into it from 2, 2 to 5, from 4, 4 to 5, um, 2 to 5, 4 to 5, 7 to 5. Leaving node 5 back to 2, back to 4, and maybe to 7. Wherever I go, the number of times in, number of times out have to match. 6 is my last internal node. Coming into 6 from 3, from 4, from 7. That has to be compared with leaving, going out of 6. Leaving 6 to go to 3, to go to 4, to go to 7. They have to match again. Let's do node 7, which is my final destination. If I compare how many times I come in, well, which ones can come in? Count how many times I go into node 7. Could be from 4, could be from 5, could be from 6, or a combination of them. Don't know. More complicated situation? Maybe. Versus leaving node 7 for whatever reason. I don't want to make any assumptions. 7 out to 4, 7 out to 5, 7 out to 6. Yes, in the simple case, I'm not leaving 7, but it might be part of a much bigger network, much slightly different problem. So having that flexibility, solver will decide that the optimal solution is to not leave 7, right? I don't make those assumptions. That's part of the solution. So how do I compare these? Well, for the terminal node, the node where I finish, the number of times in, when I compare that to the number of times I leave the node, I leave it one less because I'm going to stop there. Maybe I enter it once and I leave it never. 1 versus 0. Maybe I enter it twice and leave it only once. So I could say here the number of times I leave the node is 1 less. So in order for me to balance and make this an equation, I have to add 1 to the right-hand side, which you can compare to this over here, right? So then if I want to rewrite that, it's the same pattern. Coming into it has all positive entries, positive coefficients. Coming into it from 5, coming into it from 6, and then leaving it to 4, leaving it to 5, leaving 7 to go to 6 equals 1. The number of times I enter minus the number of times I leave has to be 1. The entries have to be 1 more. So we could delete that guy, move that so they all look the same, and then we have to do the other one. Can we do it in one go? Let's see. The number of times I enter 1, potentially from 2, from 3, from 4, minus the number of times I leave 1 to go to 2, to go to 3, to go to 4, has to equal what? If you're not sure, go back, watch the previous one. The directed case is certainly simpler because I have fewer options. In order for me to correctly convey the information of that starting node, the number of times I enter the node minus the number of times I leave the node. Well, I leave the node 1 more time than I enter it. Maybe a loop is possible. It's hard for me to imagine. I don't want to exclude that. But I leave the node more than I enter the node. So if I subtract a bigger number, I get -1. Exactly the same as here. Same reasoning. Watch that first. That was simpler. All right. My decision variables, again, have the same requirement. I don't assume that a loop is necessarily a terrible thing. Solver is going to tell me that. I don't make my own assumptions. I simply translate the information of the network into the model. The rest is for the solution process to figure out. The downside is, however, I have got way more variables than this. Unfortunately, it's gonna get a little long. Too long for me to contain everything in the screen. But let me just hide this so we can at least see the adjacency matrix at the same time. It's gonna get a little messy. Yes. So I don't want to rewrite all of this. I'm just gonna move it way over. Maybe let's just move it down here so I don't lose it, right? Because I just need to extend my table here. Now, let's get rid of all of this as well as the edges, the weight. Okay, so I'm just gonna do them in order. There's no real order here, but I like to do one row at a time. So row 1, 1 can go to 2, 1 can go to 3, 1 can go to 4. That is it. There's no shortcut here. Solver needs to see all of them. I'll put in the weights as I do them, otherwise it's going to get overwhelming. Now, from node 2, 2 can go to 1, 2 can go to 4, 2 can go to 5. Yes, I can do all of this from the diagram. For me, the adjacency matrix is nicer. It really depends on you, right? Now, from node 3, 3 can go to 1. I'm looking over here. 3 can go to 4. 3 can go to 6. And of course, you can verify that with the graph as well. Weights are 52, 37, 78. Very easy to make a little mistake here. So easy. You have to be slow and careful here. That was from node 3. Now node 4. 4 can go to 1. 4 can go to 2. 4 can go to 3. 4 is the big one. 4 can go to 5. 4 can go to 6. 4 can go to 7. Ooh. Slow and steady. Weights are 91, 32, 37, 56, 31, 28. Now it gets a little annoying. I'm going to hide some of these columns. Maybe that helps me. So now from node 5, 5 can go to 2, which is very different decision-wise compared to 2 to 5. Very different, separate decision. 5 to 2, 5 to 4, 5 to 7. Weights, 76, 56, 38. 2 more, it's not that bad. From node 6, I can go to node 3, I can go to 4, I can go to 7. Weights, 78, 31, 47, right? So easy to make a mistake here. Man. Hide some more so I don't have to scroll back and forth on my spreadsheet. From node 7, as unlikely as that may be, I can go back to 4. It's an option. Solver will explore that option. I can also go back to 5 and to 6. There's no back. I can't travel there. Weights are 28, 38, 47. Okay, now I have to unhide this. We see it goes quite a bit. Not terrible, but not great. So this right-hand side stuff, I have to put alongside it there. I want to extend my yellow cells. I'm going to make them all ones. I don't know what the answer is. Let's drag it over. For all the variables, I have input values. The coefficients are done. These are not. These are very much not. I have to redo the coefficients. And I have to redo all of this. Well, all of the formulas. The right-hand sides are the same, -1, zeros, and last one is a 1. But now I need to see the constraint equations. See, first one is a -1, zeros, last one's a 1. Okay, so those are good. Now I have to put in these coefficients to match the constraint equations. That, to me at least, is not as easy, or not easy to do from the adjacency matrix or from the diagram. Maybe you disagree, but that's how I feel. So I want to make my life as simple as possible. Okay, so node 1, 2 to 1, 2 to 1 is over here. That's it, it's a 1. This gets tedious, but no, it is what it is. There's no way around it. I've done ones that were so big, and there's no way around it. You put them in manually at some point. Then I have negatives for 1 to 2, 1 to 3, 1 to 4. Okay, that one wasn't so bad. Node 2, I'm over here. 1 to 2 gets a 1, 4 to 2 gets a 1, 5 to 2, almost off the screen, gets a 1. 2 to 1 is over here, -1. 2 to 4, -1. 2 to 5, -1. Node number 3. 1 to 3 gets a 1. 4 to 3 is over there. 6 to 3 is off the screen. I have to come back to see my equation here. 3 to 1 gets a -1. 3 to 4 gets a -1. 3 to 6 gets a -1. Okay, it's not so bad. Node number 4, that's the big one. 1 to 4, 1. 2 to 4, 1. 3 to 4, 5 to 4 is off the screen. 6 to 4, further off the screen, and I can't see the rest. 7 to 4. There it is. That was all the positives. Minus negative ones are 4 to 1, 4 to 2. Those are all close together, which is why I set it up like this. That wasn't so bad, actually. Node number 5. 2 to 5 gets a 1. 4 to 5 gets a 1. 7 to 5, you're out there. And then the minuses get ooh, 5 to 2, 4, and 7. 5 to 2, 5 to 4, 5 to 7. They're always close together. Node number 6, almost there, 2 left. Not that bad. But you can see if this was a large network, this is quite a thing. And I mean, there are other options. Solver and Excel, that's not the only option, right? It's not always the best tool for the job, but it's a good place to start. It's very handy. Can do much more than we think. Sorry, I can't multitask. Let's focus. 3 to 6. I did that one. 4 to 6. Yes. And then 7 to 6. What were the negatives? 6, 3, 6, 4, 6, 7. 6, 3, 6, 4, 6, 7. Last one. For 7, still on the screen here. 5, 7, and 6, 7. And then the negatives, 7, 4, 7, 5, 7, 6. 7, 4, 7, 5, 7, 6. Beautiful. Now I have to check this formula. It is not correct. It's using the old one. So I simply extend it. And I extend the other one. And then I check. This one has the same problem. Decision variable values, they are fixed. Corresponding constraint coefficients, we drag them, we check them. Seems good. Full selection. Check another one. Full selection. Comparison right-hand side equation values. Those are good. I think everything's good. Let's go to solver. See what we get. And more interestingly, let's reset this. See if the answer is different. Previously we had an answer that said node 1 to node 3 to node 4 to node 7. Maybe it's better. Maybe it's worse now. I have no idea. It's not necessarily going to be the same. Solver time. All right. Objective is way over here. Boom. I want to still minimize. I want to change the variable values that I colored. I color it yellow. You might have a different color, but definitely color it. Okay. Left-hand sides, all equal to right-hand sides. That's easy. Then I want my variable values to be integers. And I want to check that they are not negative. Simplex LP. Let's see it. Include the answer report if the question wants. Drag it to behind, but the answer should be in here somewhere. Let me just bring my diagram down. Now, it really depends on what these edges are. I might not be able to improve it by allowing a back and forth option between any node. Might not be an improvement, right? In this case, 1 to 3, 3 to 4, 4 to 7. It's a little boring. Still the best. Still the best. So we could write, oh, this is exactly the same. Easy. But what's now interesting is, let's say, just for the sake of argument, in the original previous directed problem, I traveled 1 to 3, 3 to 4, 4 to 7. I didn't have an option to travel, let's say, via 6. I couldn't, because of the directions of the edges, I could not go 1 to 3, 3 to 4, 4 to 6, and then 7. Couldn't do it, right? Because of the directions. Let's actually change the question, because that's where the real analysis and fun starts. I'm going to make it red so we can see the change. Let's make it super small. Let's make it 5, and let's make it, I don't know, 10. Pretty low weights in comparison to all the others. So if we now go to our first model with this directed graph, I change 6 to 4 and 7 to 6, right? Let's go to number 1. I know I have the wrong graph here. Let me just insert the right one. I changed it accidentally. It's this one. Where did you put it? Oh, there it is. Come here, sneaker. So I've now changed. I don't know if I can write on this. Let's see. Yeah, I don't know if I can. I can put a circle around it. Don't know if I can write numbers on it. Let's put a little circle around this guy. I changed that one. And hey, stop. Do it again. I'm just playing now. I'm sorry. And I changed that one. Okay, 5 and 10. We'll just remember it. Okay. So everything's the same, except in my adjacency matrix, I have to update 6 to 4. We said 5. And 7 to 6 is 10, we said. Objective function is the same. Not the same. No, objective function is not the same. What am I saying? Let's highlight these guys. I changed them. Let's make them, just do that, red. So where are those variable coefficients? 6 to 4. 6 to 4, you're over here. We change that to a 5. And 7 to 6, we change that to a 10. Right? Hopefully everyone is following what we're doing here. Minor changes as the weights change. My roots and my directions do not change. So the constraints do not change at all. I'm still allowed to enter and exit the same way. So I just want to update 6 to 4, 7 to 6. 6 to 4 now gets a 5, 7 to 6 gets a 10. We will highlight them red just so we can remember. Okay, so not much changed. Now we have to rerun solver. I'm just going to reset it all. You know, it's good practice. Set the objective there to a minimum by changing these variables. Add some constraints. They're all equalities, so that's pretty straightforward. I can do them all in one go. The variables should be integers. I check the box, check simplex, go. I'm not going to worry about the answer report now because the solution is in this yellow one. And you might say, well, of course, it's not any different. It's the same. 1 to 3, then 3 to 4, then 4 to 7, just as expected, right? Because these edges are useless to me. I have a path that's very nice. There's no point in getting out of 7 just to use these edges. It's not better. There's no way to use them. Okay? The optimal solution is still the same. Nothing has changed. Okay, that's fine. Let us now go to the second one and do the same thing. 5 and 10. Not 10 or 12, just 10. Everything's exactly the same, right? In what we're changing. So let's go over here. I will move it up and I will draw some little circles because it's fun. I can't write on them, or maybe I can, I don't know. Right now, I'm not gonna try and figure this out. We know 5 and 10. It's cool. We'll remember. Don't worry about it. Now, 4 to 6 changes to a 5, and 6 to 4 also changes to a 5. Let me just color that red, and that one is, come on, change. That one is also red, right? That was the update, those weights, because I had two directions now, two places the weights change. 6 to 7, 7 to 6, same issue. That becomes a 10, and that becomes a 10. I will color them both so we can remember that we changed them. So yes, in the objective function, it does change, but those weights weren't explicitly written down. They're just referencing the adjacency matrix where I already changed it. So that's nice. Constraints do not change at all because the constraints tell me how I can travel. It's got nothing to do with the weights, which is the only thing I changed. However, I do need to manually put in the objective function here. So it was 4 to 6 was a 5. 6 to 4 was a 5. 7 to 6, 6 to, no. 10. 6 to 7 was also a 10. Let us highlight those so there is no confusion of what we changed. None of the bottom stuff changes. Let us see if the root changes. Solver time. I'm going to reset it all. Objective functions over here. I want to minimize by changing my variables, which have entries, all these yellow guys. I want to add some constraints. Yeah, I do. All the blue ones equal to their respective right-hand sides. Add that. And then, of course, my integer constraint, because that matters. Integer. Check the box, because they can't be negative. Simplex LP solve for me. Now, you can show the answer report depending what the question wants, but if you don't change anything, the variable values are updated to the optimal solution. So we have now, I'm going to write in red because that's what we changed. Am I writing in red? I don't know if I am. Node, oh yeah, I am, okay. 1 to node 3. Yeah, okay, that's not very interesting. I already established that's the best one we can do in terms of exiting node 1. Previously it was node 3 to 4. Does that change? No, that doesn't change either. Okay. I'll go to node 4 because looking at where I am at node 3, node 4 is by far the best option, right? Previously to node 4, I went 28 straight to 7. Let's see if that is the same. No, it's not. Look at this over here. I'm going to node 6 next. And then, surprise, surprise, I'll go to node 7 from there. Node 7. For total weight, I want to write in red. Total weight, or cost, if you will, of, oh, it's improved. It's 104. I have saved some distance, time, whatever the cost might be. So let's recap. Previously, the direction didn't really allow me to utilize these very cheap edges, because if I'm at 4, they're just not working, right? Couldn't utilize them. By changing these weights, the optimal solution, the shortest path, didn't change. But in an undirected case, I have way more options. I could travel back and forth as I want. And now I can better utilize these cheap uh, edges. And instead of going 1, 3, 4, 7, I can go 1, 3, 4, 6, 7 and save across these two versus the 28 that I had to do previously. So this just illustrates that the directed from the undirected case don't always have the same optimal solution. It depends. It depends on the edge weights. It depends on the directions. If these directions were different, well, that might be a different story. It depends. Every situation is different. But hopefully this gives you a good base, a good idea to build on. I could add to this by saying, oh, what if I have to go through node 2? I just changed the constraints in terms of the traveling in to traveling out. Now I will say in general, it's not quite as simple as that. If you start adding restrictions and things to this network and how you should be traveling, things get very complicated very quickly. But for our level, it won't be far beyond this. All right, that is the end. Hopefully this helped. And until next time, thank you.